So back to this idea of basic curves, and as I've mentioned a few times, if we know what the curve looks like, it just makes life a lot easier. Domain, range, and plus any other questions later on when we're doing integration and other pieces of calculus. If we know what the picture looks like, it can make life a lot easier. So we started with the basic curves. We know what the basic shape is. When we combine that with this idea of shifting the curves, then we can get a pretty accurate picture just by looking at the equation. So the first part of it, simply adding a constant to a function. So we know what the function looks like, but then it's got plus a constant. Well, another way of thinking of this is I'll group the c with the y. So in other words, I'll move it to the other side. So it's not with the x, it's with the y. And that explains why it's a vertical shift. Because technically, it's grouped with the y, and the y controls the range. So it's going to move it up or down however many units. When it's grouped with the x, that controls the domain. And so that's when we get a horizontal shift. Now, if ever you're unsure where it's moved to, look at the grouping and say, what would make this equal to 0? And that'll tell you where it's moved to. Right, if it's just the negative of the function, so whatever value is coming out of it, we're going to change it to a negative. So that must flip it upside down, because the positive is changing to a negative, and negative is changing to a positive. So a reflection in the x-axis. Whereas if it's function negative x, now it's the x values that are changing positive to negative, and so we have a flip vertically. Is that vertically? Horizontally. That's a horizontal flip, isn't it? Yeah. Horizontal flip. So it reflects in the y-axis. So something like this, say, and it can be useful, and I did it the other day, you might remember, when I had a quadratic and I wanted to draw it, and I did it by completing the square. Because when it's in that form, it tells me a lot. I can see that it's x squared, so it's the basic curve, it's the parabola, but there's some shifting happening. We're going to shift 3 to the right. Ready? Whee! Oh. Hey. Hey. But then, it's going to go up 4. And there's our new shape. And the vertex, of course, is at 3, 4. Okay. But we could do it with other shapes too. Even my dodgy cubic. So, my dodgy cubic. There it is. Y equals x cubed. I know that I'm going to reflect in the x-axis because it's negative the function. So it's not the x that's negative, it's the function that's negative. And so, whoop, there we go. Reflect. Then shift left 1 unit. And up 2 units. And so then our origin, what was the origin, is now minus 1, 2. So that point of rotational symmetry has moved to minus 1, 2. Whoa, let's look at this one. This is a bit trickier. It's a circle, by the way. We know that because the x is squared and the y is squared and the coefficient is the same. But in order to see what it looks like, I'm going to have to complete the square on both the x's and the y. So I know I'll have half the coefficient of x, which is 1, so x plus 1 squared. Half the coefficient of y, which is negative 2. And of course, I can't just change the question, so I'll add those squares to the other side as well, and we end up with 9. So I now know I've got my circle, basic circle, x squared plus y squared is 9, but shifted left 1 unit, and this time it is grouped with the y, so it's a bit more obvious that that's a y shift, and it's going to go up 2 units. Remember, whatever makes it equal to 0 tells you the shift. Y minus 2, it would be 2 that makes it 0. So up, positive 2, and there's our circle. All right, my exponential, 2 to the power of negative x. Now this might seem a silly one, but I can still apply the idea because the basic curve would be 2 to the power of positive x. It's the x that's negative, so that's our horizontal flip. So we'll flip that way, and there's my 2 to the power of negative x. All right.